So next for sound, we're actually going to look at changing the speed of sound. So we're going to start looking at the speed of sound a little bit. And I mean, the speed of sound we've used a lot so far has been around 340, which is fine. But the speed of sound isn't constant. And it depends on lots of things. Now, of course, if you remember, sound travels because you have vibrating particles in the medium, whatever the medium has to be. So if you can change the nature of the particles, you change the vibrations, you can change the speed of sound. So it depends on the actual particles themselves. For example, the type of particles, the speed of the particles, spacing. There's a whole bunch of different things that affect how fast sound can travel based on the particles. Even just simple things, for example, like we've done, for air, we've been using around 340 meters per second. Well, sound also travels in water. And in water, sound travels at around 1,500 meters per second. The particles are a lot closer. They don't have to go as far to make contact with the next particle and a whole bunch of other stuff. And that's one of the reasons sound travels so well in water. I mean, think about like whales and stuff like that. When whales sing, I mean, you can hear the whales from like huge distances really, really well. So it makes a big difference. Even that's a liquid. Even if you go to a solid, like for example, like something like iron or something like that, you're probably looking around 5,000 meters per second. The particles are really close together. They're very rigid. The elasticity of the particles and their structure, the rigid structure, it all makes a really big difference. Now, for what you guys do, we mostly just focus on air because obviously most of the sound that we deal with has to do with air. And one of the biggest things that changes things like how fast air particles are moving or how far they are spaced apart and that type of stuff is temperature. Temperature has a big effect on air. Now, there's other things that we can look at as well, but things like humidity and temperature and the density, all these different things, these things all change. We'll focus on temperature though because it's such a common one. So if we look at it, it's kind of neat how it works. It's actually a really, really simple relationship. But if we take our baseline, if we look at our baseline temperature, that is 0 degrees Celsius. And at 0 degrees Celsius, the speed of sound is around 331.5 meters per second. Now, the cool thing about it is when you start changing the temperature, the speed of sound changes in a linear relationship. It's actually really predictable. So if you actually would sort of graph things out and you had the temperature here and speed of sound here, at 0 degrees Celsius, you actually have a y-intercept of 331.5. And then as you increase the temperature, the speed of sound actually goes up in a linear relationship. And what you find is you can take that right there, and the slope of that line is 0.6. So if we go back to your basic grade 9/10 math, if we do the whole y equals mx plus b slope-intercept type thing, this is what it's for, we can actually piece things together. Now, our y value, that's our speed of sound, that's on our y-axis. So the speed of sound is equal to, the slope you find will be 0.6. The x value is our temperature, and we use a capital T. I know that's also for period, but it's really common to use a capital T for this temperature. And then plus our y-intercept, which is at 331.5. So it's a beautiful, nice little linear relationship, so it's really easy to work with, whether it's positive or negative temperatures. And it's really easy to calculate the speed of sound at any temperature you want. And even if you take like room temperature of around 20 degrees or so, well, 20 times 0.6 will give you 12. And the 12 plus the 331.5, you're looking around 343 and change. So around 340, which is about how fast sound travels at room temperature. Okay, so we can use this really simple expression in order to calculate the speed of sound in any temperature that we want. So let's just look at a couple simple examples using this and see what we can come up with. Okay, so get rid of that. Okay, so we do live in Canada, where it can be kind of cold. So let's say you're outside and you're out here and you're a little kid and you're building a snowman. We'll give you a little toque for warmth. There you go, something like this. Okay, and maybe somebody yells at you to come inside or do something else, whatever it is. Okay, and let's say they are 18 meters away from you, and let's make it cold outside. It's winter time. Let's say it's minus 25 degrees Celsius, and we're going to see how long to hear the person so you can ignore them. All right, well, first of all, let's just find the speed of sound. The speed of sound is 331.5 plus 0.6t. It's typically written like this with a 331.5 first. Okay, so I've got the 331.5 plus 0.6t. The t is negative, so it'll end up being a negative number, which is going to drop our speed of sound. And that would be negative 15. All right, so it'll end up being a subtraction, which makes sense. So we got 331.5, take away 15, leaves us with 316.5. So there's the speed of sound. Okay, well, now to find out how long it would take, well, I can just use good old-fashioned DTV. That'd be the distance divided by the speed of sound. Of course, the distance is that 18. So we just got to take that 18 and divide that by 316.5, and it's going to take 0.057 seconds for you to hear them. Okay, so that's it. I mean, it's relatively simple. It's not too complicated, nothing too strange or weird. Okay, so let's take something else. Okay, suppose, let's do something really, really similar. Okay, so suppose, get some grass here or something like that. Okay, here we have, so just draw a little dog or something like that over here. Little tail, wagging away. Looks like a big puffy dog, actually. Alright, so alright, something like that. Give or take a little bit, a little eye. Ooh, that's a creepy looking eye. Let's change that. Alright, so we'll put the eye over here. There's a little nose. Alright, so the dog's barking at you and startles you a little bit, so oh no, dog. Okay, so let's do something really simple here. Okay, so let's do something really close. So let's say the dog was 26 meters away from you, and you hear the dog. In, let's go with 75 milliseconds. So 75, not meters per second, 75 milliseconds. So 75 to the negative 3 seconds. And we want to know what is the air temperature. Okay, well, let's see. We got distance and we got a time. Distance and time, we can find our speed of sound. So speed of sound, again using basic DTV, speed of sound would be the distance divided by the time. Don't forget to change the milliseconds into actual seconds, and we can divide the two out. So you got the 26 meters, and we'll divide that by the 0.075 milliseconds, and we got around 346.7 meters per second. So it looks like it might be kind of warm outside. Okay, so we know that for speed of sound, we got 346.7 is going to be equal to 331.5 plus 0.6t. So relatively easy to solve for. We just got to isolate the t, and this is a good old-fashioned grade 9 algebra. And we can divide the out with the 0.6 after you do a little subtraction. And we're looking around, well, give or take, the temperature is going to be around 25 degrees outside. Okay, so that's how we can find the speed of sound based on the air temperature, which fluctuates a lot. I mean, you think about Really cold day here, minus 30 in the winter. Really hot day here, plus 30 in the summer. That's a 60-degree difference between cold and hot between the seasons. 60 times 0.6, that's like 35, 36 meters per second. I mean, that's about a 10% difference. So the speed of sound around here actually changes by like about 10%, whether it's winter or summer.